All right, how much work is needed to stop a merry-go-round with a certain mass, certain radius, rotating it? Here's the key thing. One revolution rotates it one revolution for every 7.4 seconds. I think you know that you've got to convert that. One revolution is, of course, 2 pi rad. And so let's do that. 6.28 divided by 7.4 equals 0.8486 radians per second. Now, how much work does it take? Well, how much work does it take to stop something moving? It equals the change in KE. So we know we're going to get negative work because there's a negative change in KE. It ends at 0, and then the initial KE is all we have to find. So I'm going to need a lot of room for this. KE is it's rotational KE, so it's 1/2 I W squared. And we're told that in the problem that the moment of inertia we're given is mr squared. The W we can actually find, actually we did find it, it's right over here. So now it's, oops, that's squared. So now we just have to substitute it in. 1/2 times 1/2 is 1/4. M is given as 1850 kg. And R is given as 8.30 meters, that's squared. And then the W that we found, 0.8486 radians per second, that gets squared. And when you work it all out, you get a work equal to negative 2.30 times 10 to the 4th joules. And the power, what kind of power is exerted? Well, that's pretty simple, because power is simply equal to W over T. We have the W, we have the work, and we were told in the problem that it was slowed in 7.4 seconds. So we just take that W we have, I won't rewrite it, the W you have before, the W that's in your calculator, and we divide it, we get, let's see, we get, I'm going to do it again, 2.3 times 10 raised to the power of 4 divided by 7.4, 3.1 times 10 to the 3rd watts of power. Okay, that was an interesting one. 7, a thin hoop. It's got that big moment of inertia. They've got a mass, we've got a radius without slipping. This is one of those problems we've done before. You've got an incline. Since there's no mention of motion, we assume it has no motion. But it does have MGH, and at the bottom it has translational kinetic energy and rotational. So what are we looking for? What is it, the speed at the bottom? So we've done this before, so this shouldn't be new. It's whenever you have a change of height or change in speed, you think of conservation of energy. mv squared 1/2 I W squared. Now you got rotational stuff, you got translational stuff. Let's put everything in terms of translational by using our trick. Let's go over that again. So I'm going to start over here. MGH equals 1/2 mv squared. That's good. Plus 1/2. We're given a moment of inertia of mr squared. So I substitute in. We have W, and here's where we go. V squared over R squared. And all the m's cancel out. That shows you mass doesn't matter with rolling. And you know what else doesn't matter? The radius. Oops. This should be V squared over R squared, because W squared equals V squared over R squared. Love that the R's cancel out, so radius doesn't matter either. It turns it to be GH equals 1/2 V squared plus, just 1/2 V squared. So let's see if that's correct. Looking over here, good. GH equals V squared, and V is radical GH, which is radical 10 times the height that they give us. So radical 6.7. And when you take the G times the H, and it's 2.6 meters per second. There you go. And that's we've done that before. And I think we'll do, like I said, there's repetition. That's why I'm stopping on the first three. So 2 cylinders, both are 1/2 mr squared, roll without slipping down an incline. There's a height. You have a sphere. 2 solid. So that's funny. 2 solids with this decline. Sphere 1. That's funny. They call them 2 solid cylinders. Sphere 1. Then they're saying sphere 1 and sphere 2. Oh, which cylinder? That's funny. They've mentioned 2 solid cylinders. Yeah, and they say sphere 1 and sphere 2. That must be an error. So we're going to just go with what they want. This actually is 1/2 mr squared is the moment of inertia of a cylinder. So that's a mistake. That should be a cylinder. Let's go like that. It's a good thing we did this together. Should be cylinder 1 and 2. Which cylinder gets down to the bottom quicker? Well, they have different radiuses, different masses, but we've been learning that that doesn't matter. And I'll show you how that works again because we just did it. So mgh equals 1/2. So at the bottom, at the top, it's only mgh. That's the only energy it has. There's no mention of motion. So we assume there is no motion. When it gets to the bottom, it has translational kinetic energy and rotational. And then we clean this up, mgh, clean it up and find out that the m's cancel out and the r's cancel out. Let's put in that. Yeah, that is definitely a cylinder's moment of inertia. So sphere should be cylinder 1 and cylinder 2. Instead of w squared, we do v squared over r squared, which we love to do because then the m's cancel out. So mass doesn't matter and radius doesn't determine the velocity at the bottom. So it goes gh equals 1/2, just like before. Wait a second, no, 1/2 v squared plus 1/4, 1/2 times 1/2 v squared. And so we've done a problem like this before. 1/2 plus 1/4 is, let's see, 2/4, that'd be 3/4. gh is 3/4 v squared. Multiply both sides by 4/3 to clean that fraction. 4/3 gh radical, because we square it. And that turns out to be, when you plug the numbers in, 3.3. They're both 3.3 meters per second. Let's write both. Because, what do we say? The m's cancel out and the r's cancel out. We've done this enough, so maybe you know that. I think we're going to stop because, like I said, I could do more. But I don't think this one's kind of interesting. I don't know if there's so much different. What's the total kinetic energy? That's just translational, 1/2 mv squared, plus rotational, 1/2 iw squared. What about this one? What is the rotational kinetic energy? That's 1/2 iw squared, and you've got a w. So I think we're going to stop right here.